Good day, I'm Norman Wildberger. Today we're going to be looking further at base 2 vexils, looking at the arithmetic with base 2 vexils. So we're trying to understand Hindu Arabic numerals from a vexil point of view. The idea is we're just extending our understanding of vexils a little bit to incorporate the idea of numerals. And today we're going to be concentrating on base 2 vexils, but it's not a big jump to go from the base 2 situation to the base 10 situation. So I remind you that this notion of vexil is a very fundamental and flexible kind of notion. It's a multi-set of singletons. And this actually sheds new light on our earlier theory of polynumbers, because vexils and polynumbers are effectively pretty well the same thing. So we can kind of bring together two different kinds of mathematical objects now into a single framework. So what is a vexil? Well, here's an example. Vexil V, it's a multi-set, and it has a lot of these singletons in it. A singleton is just a little list with one natural number in it. And these natural numbers that appear here, these are primitive natural numbers. So if we actually looked more carefully or closely at this too, we would see a little m set of strokes. 1, 1. All right, so that's a vexil. And we've seen that we can also express it, well, perhaps in this Fries kind of notation as a column vector, which is really effectively the same thing as what we were talking about earlier, polynumber, where we have a string of coefficients written vertically. And I remind you that this polynumber also corresponds to this polynomial kind of expression, 2 alpha to the 0 plus 0 alpha plus 3 alpha squared plus alpha cubed. And it's worthwhile to really appreciate that a polynomial like this is now really being associated to this arguably more fundamental kind of data structure situation. So the 2 alpha to the 0, which is just like 2, corresponds to these two 0 singletons. 3 alpha squared corresponds to these 3 singletons of 2. And this alpha cubed corresponds to this singleton of 3. So we're employing our multi-set point of view to understand polynumbers. Now, one of the big advantages in thinking about things this way is that vexil arithmetic is very elementary, because we're just working in this very pleasant framework of multi-sets. So addition, for example, is just m-set addition. Here's a vexil, here's another vexil. So in order to add this m-set and this m-set, we just put all the singletons into a bigger m-set. And multiplication is also interestingly easy in some way. It's the m-set extension of the following essential product of singletons. So it's a rather novel product of singletons. The product of the singleton n with the singleton m is by definition the singleton n plus m. And then when we want to multiply two vexils, we just have to employ this basic rule for each possible pair between the singletons in this m-set and the singletons in this m-set. So this 0 times this 1 is 1, this 0 times this 1 is 1, this 2 times this 1 is the singleton 3, and then the corresponding products are 4, 4, and 6. And this kind of multiplication corresponds to, on the polynomial or polynumber side, the following. So this vexil here is really, or can be thought of as the polynumber 2 plus alpha squared. There's 2 zeros and a single 2, so that corresponds to 2 plus alpha squared. This one corresponds to alpha plus alpha to the 4th. And when we multiply those with the usual sort of polynomial or polynumber multiplication, we get 2 alpha plus alpha cubed plus 2 alpha to the 4th plus alpha to the 6th. And that corresponds to this product over here. 2 alpha corresponds to these two singletons, the alpha cubed to that one, the 2 alpha to the 4th to these two, and the alpha to the 6th to this singleton 6. So this technique of pinning polynomial or polynumber arithmetic onto this more fundamental MSET framework of vexels has another advantage, that it explains a former ambiguity that we had, kind of a subtle issue that we never entirely were able to resolve. And that's the question of why adding zeros to a polynumber doesn't change it. So when we were looking at polynumbers, basically lists of coefficients written vertically, then this polynumber here and this polynumber were regarded as the same, even though the actual number of entries here was different. Somehow adding a zero doesn't change things. And it was hard to say why that was, except just to declare that that's the way it was going to be. But now we can see that there's an explanation for that in terms of the more fundamental objects of the associated vexel. So this thing here is really a representation of this vexel. 2 zeros, 3 twos, and a single 3. And when we look at this thing as the fundamental object, well, we can describe this in terms of a multiplicity list in lots of ways, in that we can also, say that there's 0 4s and 0 5s and 0 6s and so on. But it's really this object which is the fundamental thing. And note that there's no ambiguity here, really. Right? There's no things that we can add to this or take away and it stays the same. It's just this is the vexel. So for example, if you were programming, then at the level of these lists you would have to program in the fact that adding the 0 doesn't make a difference. But if your computer is working just with the MSETs themselves, then there's no need to even discuss that. So with that review, we can now look at these base 2 vexels. So we take the idea of a vexel and we add a little bit to it to get a new type of object called a base 2 vexel. And we'll denote the type by this expression, vex2. Corresponds to base 2 vexel. So this is a new type of vexel where we agree that we're going to have a further kind of exchange rule applying. So this is a rule that allows us to exchange 2 singletons of the same type, actually 2 equal singletons, which appear in an MSET, with a single singleton of the next number higher. So the singleton n and the singleton n together, they can be replaced with the single singleton n plus 1. And this is supposed to be true for any natural number. That means n equals 0, 1, 2, and so on. So for example, in vex2, here is a vexel, the same one we've been thinking about, 2, 0, 3, 1. Now if we regard this as now a vexel in vex2, in other words a base 2 vexel, then we are allowed to rewrite it. Because we can, for example, take these 2 zeros here, this 2 really represents 2 singleton zeros, and we can replace those 2 singleton zeros with a singleton 1. So the 2 here can be replaced with a 1 here, otherwise it doesn't change. And then similarly from here, we can take 2 of these, which these would be singleton 2s in our actual list. We can take 2 of them and replace them with a singleton 3. Then having altogether 2 singleton 3s. And then at the next stage, we could take these 2 singleton 3s and replace them with a singleton 4. So in vex2, each of these are actually equal. These are not equal as vexels, as ordinary vexels. They're clearly very different. But in vex2, we agree that they are all the same object. So this exchange rule allows us to have a lot of different forms for the same base 2 vexel. But we can also go the other way. So we can exchange 2 of one level for 1 of the next level, but we can also exchange 1 of one level for 2 of the previous level. So for example, here our same 2, 0, 3, 1. This base 2 vexel can also be written as 2, 0, 5. What we've done is we've taken this single 1 here, which represents a 0, 1, 2, 3, a 3 singleton, and converted that 3 singleton to two singletons, a pair of 2 singletons. Now there were already 3 2 singletons in our M set, so now altogether there are 5 2 singletons. And there's no reason why we couldn't do that again. We could take those 2 singletons and take each one and replace it with a pair of 1 singletons. So the same base 2 vexel is this one here, 210. And once more, we could replace these 10 with 20 of the previous ones, giving us just 22. So we see we have quite a range of forms for a base 2 vexel. We started with this one here. It's the one that we wrote down several times already. And we saw that we could kind of expand it out by replacing any 2's with one of the next one. If we keep doing that, eventually we get this expanded form where there's only 0's and 1's. This is what's usually thought of when we think of a base 2 number. So those of you from a computer science background will naturally be thinking that this is the object that I'm going to be working with exclusively. But we're not going to work with these things exclusively. Yes, this is a base 2 representation, but we're also going to allow ourselves this flexibility that this base 2 vexel can legitimately be rewritten in this way, or also in this way. Now this is a very different kind of form. We could say this is the compressed form, where we've pushed all of the entries up, so there's just 0 singletons here. There's really 22 0 singletons. So this is a quite interesting thing. We have a base 2 vexel, and it can be written in this expanded form just with 0's and 1's, or all of the content can kind of be pushed up here to give us just a number with a certain number of 0 singletons. Maybe I should say there's a bit of a qualification to what I just said. Right? So I said we could take a typical base 2 vexel, and we could start pushing them all up and getting this compressed form. That's certainly true in the range of smallish vexels that we're considering here as examples. But you could kind of imagine that if this vexel here was, say, trillions and trillions of digits long, instead of having 4 entries, there were trillions and trillions of entries, then pushing them all up and just getting a compressed form is not at all so trivial. Okay, because every time you take one at some level and replace it with 2 of the previous level, you're doubling the numbers. And so if you have to go trillions up, then you're basically taking powers of 2, 2 to the trillion, or 2 to the trillion to the trillion, and so on. And so you very well might end up with a situation where this number here is outside of the range that you have. Because we are, I remind you, insisting that each one of these entries here actually be natural numbers. Primitive natural numbers that we could actually explicitly write down. So we're definitely looking at things a little bit differently here. In the standard treatment of binary numbers, which is usually what base 2 vexels are called, they're always expressed in expanded form. And moreover, they're almost always written horizontally. And the usual convention is that the powers of 2 are decreasing from left to right. So the number 22, our natural number 22, is written in binary as 10110. And in this representation, this 0 represents the number of 1's, this represents the number of 2's, this the number of 4's, this is the number of 8's, and this is the number of 16's. So this is asserting that 22 can be built up by taking 2 plus 4 plus 16. And indeed 22 is 2 plus 4 plus 16. So this is the binary representation of 22. So this is the standard way of doing things, but our notation is somewhat different because we were writing this same thing vertically, starting with the ones up at the top. What's usually called the ones up at the top. So we wrote this as 0, 1, 1, 0, 1. The advantages of writing things vertically rather than horizontally are the same advantages that we get by thinking about polynumbers as vertical objects rather than horizontal objects. And this is made clear when we start thinking about the arithmetic with base 2 vexels. So let's think about that. Let's think about addition with base 2 vexels. Suppose, for example, that we're interested in the relation 22 plus 13 equals 35. Okay, so here is 22 written as a vexel, as a sort of a polynumber in polynumber form. And here is 13. Let's just check this. So this is 1, 0 2s, 1 4, and 1 8. This is 1 plus 4 plus 8. That is indeed 13. Okay, so when we add these, well, it's not surprising. We're just going to add component-wise. So 2 plus 1 is 3, 0 plus 0 is 0, 3 plus 1 is 4, and 1 plus 1 is 2. And indeed, this is the binary representation of 35, just written vertically. So it's 3 1s, no 2s, 4 4s, and 2 8s. So this is 16 plus 4 4s is another 16, that's 32. Plus 3 is indeed 35. Now, another way of writing this is in expanded form. Okay, so we could replace this base 2 vexel with its expanded form, which we've already seen, 0, 1, 1, 0, 1. This is the usual binary representation of 22, but with the 1s up at the top, 1s, 2s, 4s, 8s, 16s, increasing powers of 2 going down. This thing here is the binary representation of 13 that's already in sort of expanded form. And now if we applied the same rule here, we would get 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, 0 plus 1 is 1, and 1 plus this empty 0 is 1. So we're still doing basically polynumber arithmetic. But now to get something in expanded form, we would look at this 2 and think about replacing it. So replacing this 2 with a single 1 of the next layer. So this becomes 0, and then this thing here becomes 2. And then I've done a few more steps. So I'm going to replace that 2 that's now there with another one of these, giving us 2 of those. And then those 2 things are replaced with a single 1 the layer down, namely that one there. So this thing here is equal to 1, 1, 0, 0, 0, 1. And let's just check that that's really the same number. In binary, this would be 1s, 2s, 4s, 8s, 16s, and 32. So this would be 1 plus 2 plus 32, which is indeed 35. So this is another way of describing the addition of these things in the base 2 vexel language. But yet another way is just to write 22 plus 13 equals 35. This is also a legitimate expression in base 2 vexels, because these are also base 2 vexels. So this base 2 vexel is the same as this base 2 vexel is the same as this one. And this one is the same as this one, is the same as this one, and this one is the same as this one, is the same as this one. So all of these are valid computations in Vex 2. Even though in ordinary binary addition, we would only really consider this plus this equaling to this. Even this as an intermediate object would usually not be allowed. There's a definite advantage, as we'll see, in being a little bit more flexible about binary arithmetic and not insisting that everything happens to have zeros and ones. That's not the essential feature, actually, of binary arithmetic. Okay? The essential feature of binary arithmetic, I'm suggesting, is captured by the exchange condition. The fact that we are agreeing that 2 at this level equals 1 at this level. That's the crucial property of a base 2 vexel, or in fact of binary representation of numbers. So this line of reasoning becomes clear when we go to multiplication. Multiplication is decidedly more trickier than addition. So let's have a look at a multiplication in this sort of base 2 world. Let's look at 22 times 13, which is 286. And over here, I just made that calculation so you can check. So here's how we multiply 22 by 13. We usually write them like that. And then there's a line, and we calculate 3 times 22. In that case, it's 66. It's relatively easy to do. And 1 times 22, that's in this case also easy to do. So we put the 22 over there, sort of moved over 1. And then we add 6. 6 plus 2 is 8, and the 2 is 286. So relatively simple multiplication in that case. Now, how does the same thing look in binary? So the usual story in binary is to write 22 as 0, 1, 1, 0, 1, and to write 13 as 1, 0, 1, 1, as we've seen. And then essentially to do something like this, but sort of do it in binary. So we take this 1, so 1 times all of this. It means we're just basically copying this out, just as we copied the 22 when we multiplied by 1. And then we move over 1 to this place, and we have to multiply 0 times all of that. Well, that's just a row of zeros. And then the next one, there's a 1 here, so we have to copy this thing again, but we have to move it over so that it's starting here now. So there's the 0, 1, 1, 0, 1. And then there's one more of them, because we have to multiply by this one as well, so there's another copy right there, 0, 1, 1, 0, 1. Alright, so now just as before up here, we're going to have to add up all these columns. So here we get a 0, and here a 1, and here a 1, and here a 1. Here's the first place where something interesting happens. We get a total of 3. But in the traditional form, we're not allowed to write 3 there. We have to expand that 3, essentially think of it as 1 plus 2. So we write the 1 for the 1, and the 2 is carried on to give us a little 1 in the next column representing the 2. So the total of 3 that we got here is divided into this 1 here and this 1 in the next place up. Now the sum in the next column is 2, which we write as 0 plus a carry of 1. Then in the next column, 1 plus 1 is another 2, which is 0 plus a carry of 1. Then 1 plus 1 is 2, which is 0 plus a carry of 1. And finally, the carry of 1 comes down. And so then our total is this number in binary, which is 0 ones, a 2, a 4, an 8, a 16, no 32s, no 64s, no 128s, but a single 256. And so we see that if we add these things up, we do get 286. So this is the standard story, but it's actually quite a lot more subtle than it's usually appearing because of the relatively simple or small nature of the example that we've illustrated things with here. Okay, if we look at more complicated examples, the story gets considerably more complicated. And then it becomes clear that I think the vertical approach that we're going to show you now has some serious advantages. Okay, so now let me show you the same multiplication operation, but in a vertical form. And I think you'll start to see the advantages in thinking vertically. Okay, so here is that first number, that was 22, and here is 13. And let's multiply them in this vertical fashion. Okay, so how could we do that? Well, we could essentially do the same kind of thing as we did before. So over here is going to be the sum. And what we're going to do is we're going to multiply this thing here first by 1. And that just means basically copying this thing over here. And then we're going to multiply the same thing by 0. That basically is a column of zeros. And then multiplying it by 1 here, we're going to have the same thing, but now it's sort of displaced down 2. And when we multiply it by this one, it's the same thing, but displaced 1 more. So this is really exactly the same story that we had before, except that these things are now going down columns as opposed to going across rows. No difference. Okay, but now what we can do is we can think about these various rows. This is just the same thing as was happening in the columns before. But we can add up the things in these various rows. So here's a 0. 1 plus 0 is 1. 1 plus 0 plus 0 is 1. This is 1. Here's a total of 3. Here's a total of 1. Here's a total of 1. Here's a total of 1. So because we're, first of all, having this flexible approach about base 2 Vexel arithmetic, we're not bothered by having a 3 here. Okay, so in particular, if we wanted to, we could stop the calculation. This is a legitimate output. This is a proper representation of the product of these two things in base 2 Vexel world. But we're maybe wanting to consider this as an intermediate calculation, and then we would then carry this on to reduce it. And that would involve taking this 3, because that's the only one that's, in this case, bigger than 1. And so replacing that 3 with a singleton 1, and then 1 of the next one. Well, 1 of the next one would make that a 2, and that 2 is going to be replaced with 1 of those, which is going to be then, there's 2 of them there, and replaced with 1 of those. And there'll be 2 of those there, and replaced with 1 of the final one. So this is the same kind of calculation as before. But it has the advantage that we're working horizontally here. So suppose we were working, for example, with numbers that had columns which were very long, maybe hundreds or thousands of entries long. Then these sums that are going to be going across here are also going to be correspondingly long. Okay? And when you're doing this kind of long thing, it can be advantageous to work horizontally rather than vertically, because you have more room at the end, because you're going to be writing down a long number. Okay? So the number that you might get at this level here is some number with 37 digits. Okay? And it's nice to have room to write it horizontally. If you're forced to work in a column, then you have just this limited amount of space at the bottom of the column to write down the entry there. It's just a notational difference, but it actually is, in practice, if you actually did big multiplications, you would find that there is a difference. So this is all happening in Vexel 2. This is arithmetic in base 2 Vexels, and we can see that there's something pleasant about this, this Vexel approach to this binary operation. Right? Having this basic exchange property, which is the essential feature that distinguishes Vexel arithmetic from base 2 Vexel arithmetic, and allows us to deal with this kind of intermediate calculation, and indeed allows us to collapse something like this if we want to. So we could collapse all of this to just be 286, with a single entry 286 and nothing else below. In our next video, I want to then go to our main object of interest, which are Hindu Arabic numerals and the arithmetic of Hindu Arabic numerals. So it's much the same as what we've been doing now, but the insights that we've gotten here will have some effect on our approach to the way we set out the arithmetic with Hindu Arabic numerals. In particular, we're going to be thinking about multiplication in a little bit of a different way, following this kind of lead. So we're going to be looking at Hindu Arabic numerals and really establishing a solid foundation for them, independent of our primitive natural numbers. And we're going to be looking at multiplication with something of a new orientation. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.